Recording. And what we are going to be covering today is we're going to be talking about DNA techniques, which we talked about last time. I wanted to kind of close the loop on discussion of sequencing because that's kind of where we left off last time. And then we are going to talk about lipids for a little bit, and we will also talk about membranes. So the slide deck that I'm going to start with is titled Week 11, Day 1, DNA Techniques, and grab the link from our Canvas page, and I'll add that to the chat. So copy link. So, oh wait, just saw link the. Hello, I got a private message question. Homework 9 through 13 is over material that we have not yet covered in the lecture. Will you complete those by tonight, regardless, or will those get pushed to a later date? I'm going to bump those to a later date. So I will adjust those a little bit later today. And so, yeah. So to make that adjust dates. And I'll send an announcement out. Sorry, I'll send an announcement out over which ones are going to be changed and with the updated due dates. Just would like to make sure that exam 3 is after tomorrow. The exam 3 is on Thursday the 20th. Yes. So that has not changed. Okay, so I just added the link for the slide deck. Sorry, just got here. What did you mention? I was mentioning that there are some homeworks that I'm going to change their due dates because we haven't covered that content yet. And then the exam is still on Thursday, the 20th. The link that I just shared right here, Canvas TXT, yep, that is the link for our, just a second. Okay. Okay, so how will so the link that I just shared is for the slide deck that we're going to be working with in just a moment. Will the final exam be cumulative? Yes. How will the exam on Thursday work? What time is it? And will there be another date like last time? There will not be another date like last time. The exam, I think what I'm going to do is just open it at 8 a.m. and close it at 8 p.m. I'll give you the heads up, and I'm going to send that out detail that I was planning on talking about the exam at the end of class, but I'll knock it out right now. So the exam will open at 8 a.m. It will close at 8 p.m. If you elect to start the exam, right before, or if you elect to start the exam at 6 p.m. and you encounter a technical issue and you email me to help you resolve that issue, I'm probably not going to get that email in time. I would recommend taking the exam during a regular class period, but I know that there are some folks who have work or some other issue that influences when they take their exam and when everything goes on like that. I have a question about one of the homework. Can I ask you after? Absolutely. Are there any other questions about the exam? It's going to be just like the last one. It's going to be over exam 3 content, the most recent stuff, and exam 2 content. There are some things on the practice exam that we did not cover. I'm not going to be asking you about those things. I'll send an updated version of sort of objectives based on what we cover today and where we get today. But in the meantime, I think, you guys can ask a question as it comes in. So for the homework, we have to write them on a paper and send a picture. You are welcome to write on a tablet and submit a PDF that way. I don't really mind. I just don't want you typing. I'm sorry, could you repeat what time frame the exam will be open? 8 to 8. 8 a.m. to 8 p.m. So for homework 9 to 13, I looked up things on YouTube. Should I redo it? I feel fairly confident on it. You're more than welcome to submit those. That was a private message question. You're more than welcome to submit those. I'm going to have a new due date on some of those homework assignments. And so if you feel confident in them, stay with it. You'll be able to make multiple different submissions though. Okay, so what we were talking about most recently with respect to nucleic acids and nucleic acid techniques. Um, can you tell me, somebody in the chat, add to the chat, what is the position on a ribose sugar that really matters for um, distinguishing between RNA and DNA. 2 prime, perfect. Now, in both an RNA molecule and a DNA molecule, what is present on carbon 3 prime? Perfect, an OH. Now, that OH is necessary for the formation of what type of bond that connects one sugar to another sugar in a DNA or RNA molecule. It's not a hydrogen bond. Those OHs are present so that we can bring in something else, the thing that gives the DNA molecule its overall negative charge, and it's donated from ATP, for example, a phosphodiester bond. That's what I was looking for. So we're bringing a phosphate in. And so when we look at um, when we look at a molecule of DNA or RNA and we see a 3' OH group, then we say, okay, cool. With that 3' OH group, I can bring in a phosphate and I can make a phosphodiester linkage or a phosphodiester bond. How does everyone feel about that term, phosphodiester, and the 3' OH connecting to the 5' OH? Give me a 1 if, yeah, I feel good about that, and a L if, oh, huh? I don't know why I picked characters that are very similar in structure and shape, but okay, I'm seeing lots of ones. So that's fantastic. Now, what I want to highlight here is when you're doing PCR, when you're carrying out the polymerase chain reaction, you have three major steps. You have the denaturation or melting. You have the annealing, where your oligonucleotide primers bind to the two single strands of DNA. Then you have your polymerization, where a new DNA molecule is synthesized. Now, if you look at this model at the bottom of the screen, what I want you to see is this OH group. So here what we have is a piece of DNA that is being constructed, and this OH group is really a great place so that this phosphate right here can then replace that OH group and give us a 5' to 3' phosphodiester linkage. Phosphodiester linkage. Now, in the event that we do not have, so no 3' OH group, what's your thought on can we make that phosphodiester linkage? Y or N to the chat. If we do not have a 3' OH group, but rather have a hydrogen there. No, you're absolutely correct. We cannot make that phosphodiester linkage. So that when there's no 3' OH group, then what do you think happens to that piece of DNA, that double-stranded piece of DNA that's being synthesized? Do you think the reaction continues on or stops? S for stops or G for going on. Perfect. It stops. It arrests right there. That's why a DNA sequencing reaction is commonly known as the DNA chain terminator procedure. Terminator, or it terminates that reaction. Now let's imagine, if you will, I'm going to get a blank PowerPoint slide here. Okay, so when we're doing DNA sequencing, there are some critical differences. I already mentioned the CLINAU fragment. That's your DNA polymerase fragment, or just a chunk of that enzyme. Okay, so here's our double-stranded piece of DNA. What we're going to do is we're going to go through that separation, that denaturation. The two strands of DNA will separate. So here's one strand, here's the other strand. Now, what is going to happen next is we're going to have an oligonucleotide primer bind. So that's denoted by that blue band right there. Then we're going to have our enzyme. I'm going to draw this in green, and it's going to look for a double-stranded piece of DNA, and it's going to find it. A double-stranded piece with also a single strand. And what this will do is it will take in all of the DATP, DGTP, dCTP, and dTTP. It will use these and it will add nucleotides. Duh, 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 duh. Okay. How does everyone feel about that process? So our DNA polymerase or our CLINOW fragment is integrating those new nucleotides as it sees kind of the complementary base on the opposite strand. Give me a one if, yeah, I follow that, or a five if you're like, wait, okay. So now this right here is basically just PCR. What makes sequencing so different is within this mixture of these four deoxynucleotide triphosphates, you will have one DD ATP, for example. So you'll have, I'll just call this reaction one. So in reaction one, you'll have all of these things. And so essentially what that means is let's say the DNA polymerase or the CLINOW fragment sees a T right here. What is it going to get to complement that? Well, it's got two options. It's got DATP and DDATP. Give me a one if you follow that, a three if Y. Okay, so it's got two options. Now, ultimately, you're going to have a very small percentage or a very small concentration, a low concentration of this DDATP. Because this DDATP, if that gets integrated, so if this ends up right here, what happens to our newly synthesized piece of DNA? Can we continue synthesizing? Y or N to the chat? No. Okay. I got a question that was, why just those two? Okay. I'm happy that you asked that. The reason is because you have basically four different reactions going on simultaneously. So this is reaction one, where we have dideoxy ATP. Reaction two, you'll have, I'm just going to label it as DNTPs. So you'll have all of these. Give me a one if you're good with that, if you understand that. So we'll have all of those DNTPs, but then in this reaction that I'll just call two, what we'll also have is DDGTP. Then in reaction three, you'll have all of your DNTPs. And then in this one, you'll have DDCTP. Does anyone want to guess what we'll have in reaction four? We will have the DNTPs, but what else will we have? That's kind of the oddball. Add it to the chat. Well, exactly. DDTTP. We won't have DDATP because we already did that in reaction number one. So we'll have these four different reactions taking place simultaneously. Now, what that means is that in reaction number two, I'm gonna give a black line to separate these. Okay. In reaction number two, we're going to have the exact same. Oh, sorry, there we go. We're going to have the exact same separation of our two pieces of DNA. We're going to have then the integration of our oligonucleotide primer. It's going to complement a region of our piece of DNA. And sorry for drawing this off scale. And if it's confusing, then please let me know. But does everyone see that basically the oligonucleotide primer is going to bind to this strand right here in the identical spot for all of these four reactions? That is going to be the exact same. Does everyone follow that? Y or N to the chat? Okay. Now, what I'm going to do is I'm going to use to represent DDGTP. Well, what's going to happen is in this reaction, reaction number two, we're going to again have our Klenow fragment enzyme. It binds to the exact same spot. Same thing in reactions three and four. Those are all going to be identical. And what they are going to do is they are going to scan this piece of DNA and integrate oligonucleotides as they see fit. Okay, boom, or nucleotides. And then finally, sorry, no, my color scheme is a little screwy. So they're going to be adding these nucleotides in, boom, boom, and it's going to continue elongating until, let's say right here, there's a C. Now the Klenow fragment is, well, I can either integrate a G or a DDGTP, and it's kind of flipping a coin. Oh, and in this case, it integrated a DDGTP. So what that means is that this piece of DNA, this is the reaction will stop, and this right here is a product from this reaction. Now, in reaction three, the same thing will happen. In reaction four, the same thing will happen. Now, based on that, what I want you to think about is the size of the products that are generated. Okay, let's just go ahead and look at this one at the top. We describe pieces of DNA based on length in base pairs. So we'll say this is X many base pairs long. I'm going to say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Could you give me a Y or an N if you followed how I arrived at 12? Okay. So this is a 12 base pair piece of DNA. Now, this was the reaction number one. This is my DDATP reaction. What is at position number 12 here? Do we know what base is here? And the answer is yes, but then the question is, well, how do we know? Well, we know because this reaction used our three deoxynucleotide triphosphates and DDATP. So if the reaction stops at any point and we get a product of a specific length, we know that where that product was halted, there is a T. Does everyone follow that? Y or N to the chat. Okay. Now I'm going to go down to reaction number two, and then I'm going to flip to the next slide, and we're going to look at kind of what a result would look like. Okay, so reaction two, we've got, let's see, a piece of DNA that's been synthesized. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, this is 10 base pairs. What is at position number 10? Well, this is my DDGTP reaction. Based on this arresting or stopping at the G or at the introduction of a DDGTP, well, then I know that this is a C in that position. Can you give me a 9 in the chat if, oh, okay, I follow that. You relate the size of the products to the reactions, and that tells you some information. And then any other character if I'm confused. Okay. Now, what I want to do, and I'm just going to tackle this right here. So, the principle or the important parts about DNA sequencing. One, you sequence one strand of a double-stranded piece of DNA at a time. One strand at a time. Okay, so that's one important part. Two, you run 4 reactions simultaneously. Simultaneously, but separately. But let me rephrase that. In separate I'll say in separate tubes. Okay. Then number three is many products are generated. Are generated and product product length plus specific reaction tells you bases at specific spots, specific locations. Okay, now what I want you to do is temporarily ignore most of what's on the top of the screen. What I want you to focus in on is I want you to look at this right here. This is the mixture for one reaction. We'll call this our A reaction. This is a mixture of our nucleotide triphosphates plus our 1-dideoxy, designated as our C reaction, our G reaction, and finally our T reaction. You want to keep these separate. Now, what this allows you to do is make what's known as a sequencing gel. And with this sequencing gel, you read it Drake style by starting from the bottom. And what you're going to do is you're going to make sure that each one of these lanes is labeled. This is my A, C, G, and T. Now, tell me okay, so the things that are at the bottom of a gel, of a DNA gel, those are going to be your smallest pieces of DNA. The smallest products that are generated. Now, like I said, we're looking at this by starting at the bottom, and we're going to say, okay, well, the first product of all of these is from my C lane. Okay, so what I'm going to do is I'm going to kind of construct what is the sequence of my piece of DNA. I'm reading it from the 5' end to the 3' end. And I'm going to say, well, my first product was in the C reaction. Second one was in the C reaction. And you are going to read this out and construct a sequence based on which bands are at the lowest point of the gel. So you're going to say lowest band is C. So I'm going to say C. Next lowest is C. Next is A. Next is, add it to the chat, which base is going to be in my fourth position right here. T. Okay. Now, after that, I'm going to say, all right, well, I got to go here, here. So that's C, G, then T, T, G, A. Can anyone tell me on a scale of 1 to 5, does this make sense? Why you run 4 different reactions? One being, I understand why you'd run these 4 reactions and run them separately. And a 5 being, what? I know that that's not really a spectrum. That's more like binary options. But this is what you do. This is how you can kind of terminate reactions and look at products. Now, this type of sequencing is something that's a little bit of the past in the sense that this is a technique that was used. Oh, great. So this was, I would say it was probably my graduate advisor started his PhD in 95. Um, so does DDATP tell you where the A is? Yes. So you just read it from the bottom all the way up. I mentioned my graduate advisor because he started his PhD in 1995, finished it in the year 2000, and this was one of the first things that he did as a graduate student. I started my PhD in 2006. I never did this. So this is like, it's a fundamental topic. It's a fundamental concept to understand how it is done because why does ours not match the one on top? Or does that one not matter? Okay, thank you very much. I got a private message question that asked about what's at the top. Okay, so what we're doing at the top of the screen, I'm happy that that was asked and I've neglected to mention it, was okay. So what I want you to look at is we are basically constructing this new piece of DNA. This primer is the part that's like known. You know the sequence of that. Now, the G and the G there, that is not something that the Klinow fragment added in. Instead, the Klinow fragment is going to look at the template. But the template is, and this is where it gets a little bit hairy. It's like, well, we're constructing the complement of the template. So we want the template, but we're not trying to determine the sequence of the template. Okay. So the Klinow fragment looks at the template and says, okay, well, here's a G, and I'm going to introduce a C. Oh, in one reaction, I added in a C with that DDCTP. Then I added another C. Then the A complements the T, T complements A, C complements G, and so on. Does that make sense? Or did I lose anyone whenever I was trying to explain that? So, yes, the primer is not going to. Thank you very much for that question. That was a follow-up question. Was that so it just cuts off the primer part? Yes, because the primer is the Klinow fragment, the DNA polymerase is not making that. So you're not going to have that product there. Thank you very much for asking that. And I hope that makes sense. I hope my explanation was clear. Okay. So this is a technique that's, I don't want to say that, oh yeah, it's completely outdated, but this is, well, it's the foundation for the way that DNA sequencing is done now. Rather than running a gel and looking at products of different lengths, instead, you have oligonucleotides that have radio labels or fluorescent labels. So if you ever sequence anything, a piece of DNA, you'll get an output like this. And then you'll just say, okay, well, this was shot with a laser, and based on what base was introduced, boom, 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 that is the sequence of my DNA. Okay, so the things that I want you guys to know with respect to sequencing and PCR, I want you to know what makes PCR and DNA sequencing different from one another. For starters, the DNA polymerase. You're using the Klinow fragment whenever you're doing sequencing, whereas you're using a complete, not a fragment, but a complete DNA polymerase whenever you're doing PCR. The biggest difference, however, between sequencing and PCR is the presence of a dideoxynucleotide triphosphate, because that dideoxynucleotide triphosphate stops the reaction, which is arguably good whenever we're trying to look at or construct a sequencing gel. Okay, so now what I'm going to do is I'm going to add, let's see, get the link, copy link address, go to chat. I'm going to send this link right here is our link for our discussion of lipids. So that slide deck, which I am opening up right now and going full screen on, coming soon. And you know what I'm going to do? I'm actually going to stop this recording so that I can have a separation between the conclusion of DNA